You think the speed of light is just a number. 299,792,458 meters per second. Fast, really fast. The fastest thing we know. Fine. But why is it the limit? Why can't you go faster? What stops you? Most people have never really thought about this. They just accept it. Einstein said so. Speed of light is the cosmic speed limit. That's just how it is. But that's not an answer. That's just repeating words. When you really ask why nothing can go faster than light, when you dig into what's actually stopping you, you discover something so strange, so fundamentally different from everyday experience, that it changes everything you think you know about space and time. The speed of light isn't just a speed. It's not just the fastest thing. It's the structure of the universe itself. It's woven into the fabric of space and time in a way that makes going faster literally meaningless. Let me show you what I mean. Let's start with something simple, something everyone knows. Things fall. Drop something, it falls down. 16 feet in the first second, to be precise. That's what Galileo measured. Drop a ball, drop a rock, drop anything. In 1 second, it falls 16 feet. Now the moon. The moon is going around the Earth. It's not falling down. It's staying up there, orbiting, going in a circle. But wait, is it falling? Think about it. If the moon were just sitting there in space, not moving, what would happen? It would fall toward the Earth. Gravity would pull it in. But the moon is moving. It's moving sideways, tangent to its orbit. And because it's moving sideways, while gravity pulls it down, it keeps missing the Earth. It falls toward the Earth, but keeps missing. That's what an orbit is. Continuous falling while moving sideways fast enough to keep missing. Now here's where Newton had his brilliant insight. The moon is 240,000 miles from the center of the Earth. We're standing on the surface, 4,000 miles from the center. So the moon is 60 times farther away than we are. Newton said, what if gravity gets weaker with distance? What if it follows an inverse square law? That means if you go twice as far away, gravity becomes 4 times weaker, 3 times as far, 9 times weaker, the square of the distance. If that's true, then at the moon's distance, 60 times farther, gravity should be 60 squared times weaker. That's 3,600 times weaker. Now on Earth, things fall 16 feet in 1 second. If gravity at the moon is 3,600 times weaker, then the moon should fall toward Earth by 16 feet divided by 3,600. Do the math. 16 feet divided by 3,600. That's about 1/20th of an inch per second squared. Wait, let me say that differently. In 1 second, something at the moon's distance should fall toward Earth by 1/20th of an inch times 3,600, because we're talking about the square of time in the formula. 1/20th of an inch times 3,600 equals 16 feet, exactly what we measure on Earth. Newton calculated how far the moon should fall toward Earth in 1 second if gravity follows an inverse square law, and it matched perfectly. The moon is falling at exactly the rate Newton's law predicts. This was huge. This wasn't just a theory. This was a prediction. Newton took a completely independent fact, how fast things fall on Earth, and connected it to another completely independent fact, the period of the moon's orbit and its distance from Earth. Two things that seemed totally unrelated suddenly became connected by one law, the law of gravitation. There was no going back now. Newton went further. He calculated what the shape of planetary orbits should be if gravity follows an inverse square law. And he found that it should be an ellipse. And guess what? Planets do move in ellipses. Kepler had already measured that. But Kepler didn't know why. Newton explained it. He got 3 for 2, as it were. And then more things fell into place. The tides. Why are there tides? Because the moon pulls on the Earth. But wait, if the moon just pulls the Earth toward it, there should only be one high tide per day, right? The bulge of water on the side facing the moon. But there are 2 tides per day, every 12 hours roughly. Why? Some people thought the Earth was pulled away from the water. Others thought the water was pulled toward the moon. Both were sort of right, but neither got it completely. Newton realized what was really going on. The force of the moon on the Earth and on the water is the same at the same distance. But the water on the near side is closer to the moon than the Earth is, so it gets pulled more. And the water on the far side is farther from the moon than the Earth is, so it gets pulled less. So you get 2 bulges, one where the water is pulled more toward the moon, one where the water is left behind because the Earth is pulled more than that water. 2 tides per day. Actually, the Earth does the same trick as the moon. It goes around the circle. The center of the circle is somewhere inside the Earth. The Earth and moon both orbit their common center of mass. If you wish, this water is thrown off by centrifugal force more than the Earth is, and this water is attracted more than the average of the Earth. At any rate, the tides were explained, and the fact that there were 2 a day. A lot of other things became quite clear. Why the Earth is round, because everything gets pulled in. Why it isn't perfectly round, because it's spinning, so the outside gets thrown out a little bit and it balances. Why the sun and moon are round, and so on. Now, as science developed and measurements were made ever more accurately, the tests of Newton's law became much more stringent. The first careful tests involved the moons of Jupiter. By careful observations of the way they went around over a long period of time, one could check very carefully that everything was according to Newton's laws. And it turned out not to be the case. The moons of Jupiter appeared to get sometimes 8 minutes ahead of schedule and sometimes 8 minutes behind the schedule, where schedule is the calculated values according to Newton's laws. 8 minutes! That's a huge discrepancy. Something was wrong. But wait, it was noticed that they were ahead of schedule when Jupiter was close to the Earth, and behind schedule when Jupiter was far away. Rather odd circumstance. Mr. Romer, having confidence in the law of gravitation, came to an interesting conclusion. It takes light some time to travel from the moons to the Earth, and what we're looking at when we see the moons are not how they are now, but how they were some time ago, the time it took the light to get here. When Jupiter is near us, it takes less time for the light to come. When Jupiter is farther, it takes longer. So he had to correct the observations for the differences in time. And by the fact that they were this much too early or that much too late, he was able to determine the velocity of light. This was the first demonstration that light was not instantaneously propagated. Think about what just happened. We found the speed of light not by measuring light directly, but by having confidence in the law of gravitation. When something didn't match, instead of throwing out Newton's law, Romer said, "What if light takes time to travel?" And he was right. I bring this particular matter to your attention because it illustrates something. When a law is right, it can be used to find another one. By having confidence in this law, if something is the matter, it suggests perhaps some other phenomenon. And if we had not known the law of gravitation, we would have taken much longer to find the speed of light, because we would not have known what to expect of Jupiter's satellites. This process has developed into an avalanche of discoveries. Each new discovery permits the tools for much more discovery. And this beginning, it's the beginning of that avalanche which has gone on now for 400 years in a continuous process. And we're still avalanching along at high speed at this time. But here's the thing. Once you know the speed of light, once you measure it, you start noticing something very, very strange. Light always travels at the same speed. Always. No matter who measures it, no matter how fast you're moving. Let me make this concrete. You're standing still. You shine a flashlight. You measure the speed of the light coming out. 299,792,458 meters per second. Fine. Now you get on a train, a fast train, moving at, say, half the speed of light. You shine the flashlight forward in the direction the train is moving. Common sense says the light should now be traveling at the speed of light plus the speed of the train. Just like if you throw a ball forward from a moving train, the ball moves faster than if you threw it while standing still. But that's not what happens. You measure the light, it's still traveling at 299,792,458 meters per second, exactly the same speed. You say, okay, maybe I measured wrong. So you get the train going even faster, 90% the speed of light. You shine the flashlight forward again. You measure, still 299,792,458 meters per second. You get frustrated. You get the train going at 99.9999% the speed of light. You shine the flashlight. You measure, still the same speed. The speed of light does not add. It doesn't combine with your speed. It's always the same, no matter how fast you're moving. This should break your brain. This is not how speeds work in everyday life. Speeds add. If you're on a train moving at 50 miles per hour and you walk forward at 3 miles per hour, you're moving at 53 miles per hour relative to the ground. But light doesn't do this. Light always moves at the same speed relative to you, no matter how fast you are moving. Why? Einstein realized what was going on, and it's so strange, so contrary to common sense, that even now, over a century later, people struggle to accept it. Time and space are not fixed. They're flexible. They bend and stretch to keep the speed of light constant. When you move faster, time slows down for you. Your clock literally ticks slower, and distances contract. The space in front of you gets compressed. These effects are real. They're not optical illusions. They're not measurement errors. Time actually slows. Space actually contracts. And the amount they change is exactly the right amount to make the speed of light come out the same for everyone. Let me say that again. The universe adjusts time and space, bends them, stretches them, compresses them, to ensure that light always travels at the same speed for everyone. The speed of light is not just a speed, it's a structural constant of the universe. Space and time are arranged in such a way that this speed is the same for everyone. Now here's where it gets even stranger. If you try to accelerate something, anything, to the speed of light, something very weird happens. The closer you get to the speed of light, the harder it becomes to go faster. It's not that you run out of fuel. It's not that your engine isn't strong enough. It's that the object itself resists acceleration more and more. We call this relativistic mass increase. As you go faster, your inertia increases. It becomes harder and harder to push you faster. And as you approach the speed of light, your inertia approaches infinity. To actually reach the speed of light, you would need infinite energy, which is impossible. So nothing with mass can ever reach the speed of light. Not because of some arbitrary rule, not because of engineering limitations, but because the structure of space-time itself prevents it. Light can travel at that speed because photons have no mass, zero. Massless particles can travel at the speed of light. In fact, they must. They have no choice. They're always moving at that speed. But anything with mass, it can get close, very close. 99.9999% of the speed of light, but never quite there. The universe won't let you. Now you might ask, but why? Why is the universe set up this way? Why is there a speed limit at all? And here's the answer that's going to frustrate you. There isn't a deeper why. The speed of light isn't a speed limit imposed on the universe. It's a consequence of how the universe is structured. Space and time are not separate. They're woven together into space-time. And space-time has a geometry, a structure. And that structure has a built-in conversion factor between space and time. That conversion factor is the speed of light. It's not that light is special. It's that space-time has a maximum rate at which cause and effect can propagate. Light happens to travel at that rate because light has no mass. But the rate itself is a property of space-time, not of light. If light didn't exist, the speed limit would still be there. It's a feature of the universe itself. Here's another way to think about it. In everyday life, you think of space and time as separate things. You move through space. Time passes. They're independent. But they're not. You're always moving through space-time at a constant rate. Always. But that motion is divided between space and time. If you're sitting still, all your motion is through time. You're moving into the future at maximum speed, 1 second per second. But if you start moving through space, you have to divert some of that motion away from time. You're now moving through space and time, which means you're moving through time more slowly. The faster you move through space, the slower you move through time. And there's a maximum. If you could move through space at the speed of light, you would have zero motion left for time. Time would stop for you. This is why light doesn't experience time. From a photon's perspective, it's emitted and absorbed in the same instant. No time passes. The universe is frozen. You can't go faster than light because you can't have less than zero motion through time. That's the limit. That's the wall. And here's the beautiful part. This isn't just theoretical. We've tested this over and over and over. Particles in accelerators get accelerated to 99.9999% the speed of light. And guess what? The closer they get, the harder it becomes to accelerate them further, exactly as predicted. GPS satellites have to account for time dilation. They're moving fast, and they're in a weaker gravitational field, so time passes differently for them than for us on the ground. If we didn't correct for this, GPS would be off by miles within a day. Muons created in the upper atmosphere by cosmic rays should decay before reaching the ground. Their lifetime is too short. But they're moving close to the speed of light, so time slows down for them. From their perspective, they live long enough to reach the ground. From our perspective, they live longer because they're moving fast. Either way, more muons reach the ground than should, exactly as relativity predicts. It's not speculation, it's measured. The speed of light being a limit is as well tested as anything in physics. So let's bring this all together. Why is the speed of light the limit? Because space-time is structured in a way that has a maximum rate of cause and effect. That rate is the speed of light. Not because light is special, but because space-time itself has this built-in conversion factor between space and time. You can't go faster because going faster would require moving backwards in time, which doesn't make sense. You can't have negative time. You can't undo cause and effect. The speed of light is the speed at which now propagates through the universe. It's the speed at which information can travel. It's the speed at which forces act. It's the maximum rate of change. And this process, this avalanche of discoveries, started with Newton figuring out gravity by watching the moon. Then Romer figuring out the speed of light by watching Jupiter's moons. Then Einstein realizing that the speed of light is constant and deriving relativity from that. Then thousands of experiments confirming it, each discovery building on the last, each new insight opening doors to more insights. That's how science works. That's the avalanche that's been going on for 400 years. And we're still avalanching along at high speed at this time. The speed of light isn't just a number. It's the key. It's the thing that unlocks how space and time work. It's the thing that shows us the universe is stranger and more beautiful than we ever imagined. And the fact that we can understand it, that we can measure it, test it, use it to make predictions, that's the beauty of physics. Not comfort, not simplicity, truth.